All right, we're back. We're gonna do mammalian cleavage. Um, oh, hold on. We gotta change that. Mammalian part 3. Boom, fixed. All right. so, uh, I realized. So I put these on YouTube just because I want people that want to learn stuff for the heck of it to be able to access it. Um, Especially with the bioinformatics stuff, but also I'm surprisingly my development and my molecular biology lectures are very well viewed on there as well. Um, but what's funny is now that I'm thinking about it, I put these on there and I have all these nonsense chat GPT's images that are probably going to be like the cover photo. So people are going to be look at the slide, oh, mammalian cleavage, and it looks like an octopus. Like you can kind of see it under my screen here, but like you'll see it if you're in the class and you have the slides. But like this is nonsense. I don't know what's going on in this image, but anyways, something to amuse myself, I suppose. Okay, well, hey, it's free. It's on YouTube. It's free, so take what you can get. All right. So we've seen this image before. So the cleavage for mammalian cells starts very early. Or I should say fertilization starts very early. So you can see that we have the ovary here. We have ovulation where we are using pushing these the fimbriae or help pushing the egg into the oviduct in the fallopian tube here, and fertilization happens very far up there, and then we start cleavage all the way or down here while still inside the isthmus, or I should say the ampulla of the tube here before we start moving down. And by the time it's already a blastocyst, so pretty far in our development, by the time we get to the uterus, and we have implantation after that. So quite far along. And so let's check my notes here. So prior to fertilization, this oocyte is wrapped in cumulus cells. So we talked a little bit about that while we were doing the fertilization part of the stage. And so it's released by the ovary and swept by the fimbriae into the oviduct here. Fertilization happens during while it's kind of inside this ampulla region. Compaction of the human embryo, which we'll talk about shortly, occurs on day 4, so at the 10 cell stage. So that would be kind of right in this little region right here. So the embryo hatches or leaves the zona pellucida upon reaching the uterus. So you can see this little like kind of bubble around it is the zona pellucidae. And it will kind of leave that, and you can see it's kind of exposed or without that once it gets to the uterus here. And then during its migration to the uterus, the zona prevents the embryo from prematurely adhering to the oviduct rather than traveling to the uterus. And so that's where there's issues. There's people, like I've had a friend that has gone through this, that his wife had an ectopic pregnancy. So in cases where the zona pellucida isn't fully formed or doesn't last, or other things that may happen, implantation can happen in the uterine, and that leads to a very dangerous pregnancy. That generally the pregnancy needs to be aborted because there's not room for a baby to grow here, and so it's dangerous to the mother, and essentially both the mother and child could die if that pregnancy is allowed to continue here. So generally it needs to be down in the uterus. So mammals have a really unique cleavage pattern, and so in most organisms there's this symmetrical radial cleavage pattern. So we have like 2 different planes of cleavage, right? So kind of like a lateral and a vertical, I guess you could think of it as, or 2 different dimensions of cleavage. but then in mammal, we have this different where we have like three cleavage planes, right? So we have cleavage plane 1, cleavage plane 2A, and 2B. So it'll 3 dimensions, I guess, is the best way to put it. So after the first cleavage, one cell divides meridionally, and the other equatorially. So after one cleavage, one will go kind of depth-wise, and then one will go equatorial-wise. We're not gonna do for just know that it's 3 dimensions or 3 different planes that they divide along. I'm not gonna make you draw a picture or a model or something like that. It's kind of hard to do that on a test. So another unique aspect of this mammalian cleavage is that it's not a doubling. So generally, like we talked previously, it's exponential, where it's like 2, 1, 2, 4, 8, 16, 32, 64, etc. But that's not the case in mammals. And so there can be odd number of cells. So it would be, you could have 2, like we said in the previous slide, where compaction happens at the 10-cell stage. Well, there shouldn't be a 10-cell stage if it's exponential, right? But mammalian systems are different, where they're not all dividing at the same time. They're on separate time scales. So you can get odd number of cells, you can get non-exponential, like 10 cells, etc. So here we have kind of some microscope slides of the developing cells here. So we have A is the 2-cell stage, 4-cell. This is early 8-cell, so you can see they're still kind of dividing. And then at D here, we have what's called compaction. And so compaction is the phase, and we're going to talk about cell adhesion and things in the next unit. But compaction is where you can see it's no longer a bunch of individual cells where they're all round. They're stuck together. They're compacted into like a single ball, if that makes sense, right? So it's not a bunch of little balls stuck together. They're all making one kind of solid, compact ball. So then in E here, we have the 8-cell stage that divides to become the 16-cell morula, M-O-R-U-L-A, morula. And then F behind my picture thing here, but you'll have it in your PowerPoint slides, is the blastocyst. So like I said, at the 8-cell stage, cells start to express this protein called E-cadherin, and this is what allows cell adhesion. So instead of those round balls, like the cell walls will start sticking together and make a nice flat circle. And this allows junctions to form between the cells, and those junctions then can allow molecules and hormones and nutrients and things like that to pass in between the 2 cells. And so lastly here we have a blastocyst. So this is a small group of inner cells surrounded by a larger group of outer cells. And so you have cells along the outside here, and then cells within the inside. So the inner cells give rise to the ICM, or the intercellular mass, or inner cell mass, which will eventually give rise to the embryo. And so this trophoblast along here, this there's no embryonic structures here. So this stuff becomes the placenta and umbilical cord and extraembryonic membrane and things of that nature. Yes, so that's what is going on here. So the inner cell mass becomes the embryonic cells, and then this other stuff becomes the placenta and things like that. And later in the quarter we'll go, like I said, my wife is early childhood development and does a lot of stuff with pregnancy and stuff, so we'll see some examples of placenta, not like real placenta, but like models and things like that. So you kind of get an idea of what this really, you get to hold a model of it and stuff. Yeah, some people save their placenta after birth, and interesting, just a lot of interesting stuff with that. So that's it for this one. Pretty short, 10 minutes. So I think next we talk compaction, but this is just kind of the little nuances that are the differences between avian and mammalian cleavage and what makes mammalian cleavage kind of unique. So we'll get on to compaction, I believe, and I'll catch you in the next one.